Hello and welcome. I was wondering, what is infinite cache and why haven't we seen it before now? And I was reading up a little bit and I got interesting, and I thought maybe someone else want to see what I found out about it. I'm not really expert in the subject, but I have worked with electronics and I have a degree in electronics. I divided up the lecture in 8 parts. You can quick jump here. First, about caching basics. A CPU and a GPU both have cache. This is to handle both the bandwidth constraints as well as the latency of memory. The bandwidth is here represented by the width of the line, and latency is not represented, but the latency is pretty much comparable. The further away, the larger the latency is. Normal CPU have usually 3 levels of cache, and SRAM memory that usually DDR4 nowadays. A GPU usually have 2 levels of cache. That's actually level 0 cache, but that is not always published. So it's 2 or 3 level depending on. And memory that is GDDR is also SDRAM memory, but it's other bus type. Increasing the cache does increase the performance, but it's diminishing return depending on how much cache you have. So double the cache don't mean double the performance, but rather a slight decrease from the double. Usually now the processor have a 3 level of cache. The first level is internal cache in the CPU core, in one core. The level 2 cache is usually divided for 2 or several cores, and level 3 cache is in a lot of cases for all of the cores, but not the newest AMD processor that for now don't have cache for all cores, so it's usually for 8 CPU cores. Any processor today that have more than 8 cores don't have a cache together. For GPUs, it's a bit different. It's not straight up diminishing return, but more of a step ladder of diminishing return. In the GPU memory, there are several different types of data. Here is a few different kind of data that might be in GPU memory. A typical frame buffer, a C buffer, a render buffer, a 3D model, and texture. And in most cases, the texture takes a lot of memory, but it's not that bandwidth intensive. In most GPUs today, the bandwidth is shared between all the different kinds of data in the memory and also the capacity. So while frame buffer and render buffer use the most bandwidth, the texture uses the most memory. This is sort of a cheap solution, but it's not that optimal. To house all of the data in the cache, you need a lot of space. That depends on how large the buffer is. If we just look at one frame buffer, a typical frame buffer might take several megabytes. A 4K frame buffer in this case take about 32 megabytes of frame buffer. And in most cases, the GPU needs more than one frame of buffer, typically 3 or 4 frames of buffers. So it might need a lot of memory. How much space that would be in a cache depends on how dense the cache is, and that depends on what process is made on. If we look back at VGA back in 1995, a cache that would fit all of one frame buffer would be 30 square millimeters in size, and that would be way too much to fit, especially if you use 2 or 3 buffers. In 2000, the resolution has increased a bit. The space would need on the die to fit it would be decreased. 2005, it would be decreased a bit more, and now it's on 10 square millimeters, and that's more reasonable, but still a bit too expensive. 2010 is down to about 6, 2015 it would be about 4, and 2020 it would be 2 or 3 square millimeters, and that is reasonably small to work. And remember, that is only one frame of buffers, and they also need the logic to back it up. So in reality, that 3 square millimeters would need to be quite a bit more. This is only a theoretical number, so probably need to multiply that by 10 or something like that. There is several types of memory. Flash is currently the cheapest type of solid state memory. It's very cheap, but it's slow. SRAM is very fast, but expensive. That is usually what cache is made of. DRAM is pretty much in between. It's pretty fast and pretty cheap. Here we can see the development of the different kinds of memory over time, and how it got more and more dense over time. In future we might also have MRAM and RRAM, but it's not quite here yet. What is memory speed? The memory speed is actually the access time. The transfer speed is not limited by the cell speed. In a normal SDRAM memory, there is multiple stacks of cell in parallel that is connected via MUX. That is the S in SDRAM, and then is connected by PHY, a physical layer, is a DDR in the memory. So DDR4 SDRAM is a full name. What it states is that it uses multiple stacks of cell in parallel that is accessed one by one and then stacked out in the MUX, increasing the throughput speed but not the access time. The power usage of memory interface is basically the distance times capacity of transfer speed. The longer the distance is, the more power is needed. But also the more speed needed, the more power is also needed. That's why memory like HBM have pretty small power requirement, while normal RAM that is far away is pretty slow. Why haven't Infinity Cache existed earlier? And it's kind of already have. Back in the export 360 days, the export had 10 megabytes of external DRAM cache. And that's the chip next to the GPU here. It was sort of a cache on the separate chip that uses DRAM instead of SRAM. Slightly slower, but those so it have a high capacity. Also, the Xbox One had memory buffer on die, so it's an embedded SRAM cache. And that's pretty much what Infinity Cache is. That is only applies to the original Xbox One, not the later model that used GDDR5 instead. So does Xbox have Infinity Cache? Kind of and kind of not. It's not really the same kind of cache in software, but it fills the same function. Was put there to reduce the bandwidth need on the memory due to Xbox One used normal CPU memory with less bandwidth. That could later be removed when they switched to graphic memory with higher bandwidth. And here is the Navi21 die with its Infinity Cache. 64 megabytes of cache on each side, total 128 megabytes of cache. Memory PHY on the side. If the amount of memory interface would be doubled, it would pretty much eat up all of the cache space, increase power demands, but not be that much cheaper. So it's kind of a no-brainer to have the cache instead of the increased memory bandwidth, because then you need more memory on the board as well. And here we could see the net result. The on-board cache consumed pretty much no power whatsoever, but the PHY on the GPU side and the memory side would be practically double in power, increasing the power demand by quite a margin, around 50 watts or so. The advantage is better performance, and the board will be cheaper and it will need a bit less power. The disadvantage is that it uses slightly more die space, and for a non-specific application it might be worse. Why doesn't Nvidia use a similar L3 cache or any Infinity Cache? The reason is probably quite complicated. AMD have quite an experience with both APUs and internal cache in the Xbox consoles, and they also had a prototype APU with graphic cache integrated, but it was never sold publicly. AMD also have a lot of experience from the CPU division of caching memory. Caching don't care about context usually, but in the graphics case it might be different. Large-scale caching, large-scale graphics might need more advanced caching systems than for CPUs. Die shrinks basics. Usually the die shrinks would be in full steps and half steps. And this is how basically the die is made by a simple photolithography system. How do you make a 17 nanometer lithography with 193 nanometers light? Well, you can't. There is a few tricks to make it much smaller. You can have half wavelength exposure. That would decrease it to about 80 nanometers. And there's a trick with using water between the lens and wafer, increasing firmly about to 40 nanometers. But most of the decrease is pretty much cheating methods. They use our methods, architectural methods, to increase the number of transistors on the die without decreasing the lithography distance. This way they can fit more transistors without a full decrease in lithography length. This is pretty much how all nodes have been increased for the last about 20 years. The dominating increase in transistor count have been from our trickery. This is pretty much typical for the 32 nanometer planar transistor to the 22 nanometer tri-gate transistor, where they put them on end and therefore increase the amount of transistor by quite a lot without really decreasing the nanometer width that much. This is pretty much the end of Moore's law as we did know it, but it's the beginning of a new kind of Moore's law that pretty much have dominated the last 20 years without really anyone noticing it. It takes about 3 to 5 years to develop a GPU. Major decision would be taken first year, and the L3 cache would be a major decision. SRAM density of the TSMC 7nm is about twice that of the Samsung 8nm, but phi density is about the same. In 2017, AMD didn't look that competitive with the 14nm Video 64, and the early Video 7 show very weak gains from the 7nm process. Going from 5K to 8K output would need at least 156 megabytes of L3 cache, and 10,000 cores probably look quite unlikely back in 2017, as well as GDDR6X performance looked like it would be better than it actually would turn out to be. GDDR6X is too slow and HBM3 is too expensive. There is really not that much reasonable options today. Nvidia is probably going to use L3 cache in the near future. It will take time for them to develop it, so we will probably see it after Hopper series. What is the future benefit? One benefit of having an L3 GPU cache is that it makes possible to have chiplet GPUs. The issue with multiple chip GPUs in traditional sense is that they can't share memory, and they need to share memory to perform at highest possible performance. But with a chiplet, the amount of bandwidth used from each die can be reduced significantly to use a combined die for memory access. And that could mean that we can make a chiplet GPU in the future. And here we have a Navi20 die modified. And here how it would look if with a traditional 5nm die shrink. The logic and the cache become smaller, but the phi and the interface will not become smaller, because the size is dictated by power, not by transistor size. When the interface and the memory interface is scaled off, what is left in the chip is really just logic and cache. that scale almost perfectly with a new photography. With all the interface and PHY broken out in a new chip that might use the oldest process, this would save a significant amount of die space as well as being more optimal. The new chip might have a bit of cache too, it's hard to say. I'm just copying out the 128 megabytes of cache. It might have less, it might have more. Almost impossible to say. The cache is pretty much unavoidable. It will become in the future. It's getting cheaper for every photography step forward. L4 cache is probably coming as well, and it probably will come with chipless design. Making an APU or a mobile GPU will be much more compatible when the bandwidth amount of the memory would decrease, making APUs in the mid-range market instead of the low-range market. And it will lower the power demands, making mobile GPUs more compatible as well. Thank you.